Hello everyone, today we will be presenting our physics project on thermal expansion. We are Class C Physics Honors and my name is Katira Chokurmarkatiot and my group mates are
Martin Hongsuwong.
Na.
What exactly is thermal expansion? Thermal expansion is the tendency of matter to change its shape, area, volume, and density in response to a change in temperature. Or to simply put, objects can change in volume when the temperature changes. When a material is given a lot of heat or increase in temperature, it expands and thus increases its volume due to the temperature, making the particles of the material vibrate more and move faster, which means it takes up more space even though they are still the same size. The reverse is also the case, as lowering the temperature can cause a material to contract and thus lower its volume due to the particles moving slower and vibrating less. Though it is noted that particles still vibrate even at extremely low temperatures until the point of absolute zero. An everyday example of thermal expansion would be pavements. The cracks occur due to the increase in temperature, which results in the asphalt or concrete expanding and thus cracking. Another example is the ocean, as thermal expansion is also one of the reasons as to why the sea level is increasing. The water getting warmer makes the volume increase, as we mentioned earlier, and thus makes the sea level rise. 2/3 of the sea level rise is caused from glaciers melting, while 1/3 is caused from thermal expansion.
So this equation states that the change in volume, which is delta V, could be found by using the coefficient of volume expansion, beta, the original volume, V, and the change in temperature, which is delta T. The coefficient of volume expansion is a specific constant and differs with each material that corresponds to the item measured. The initial volume is the volume in meters cubed before undergoing any change in temperature, and the change in temperature is the final temperature subtracted by the initial temperature. The change in temperature could be measured in Kelvin or degrees Celsius. For example, the change in volume of heating up a tank of water with a volume of 2 meters cubed from 40 to 80 degrees Celsius could be found by firstly finding the coefficient of volume expansion, which is given right here as 210 times 10 to the power of negative 6 degrees Celsius inverse, and the volume in meters cubed, which is 2 meters cubed. Next, the change of temperature, which is 80 degrees minus 40 degrees, which makes 40 degrees of change. And so once you put all of those together, you find delta V equals to 210 times 10 to the power of negative 6 multiplied by 2 times 40, and you will get 0.0168 meters cubed of a positive change in volume. Next, Charles' law states that if pressure is kept constant, the volume will be directly proportional to the temperature of a given substance, and the graph for this relationship could be seen over here. Charles' law states that if the pressure is kept constant, the volume will be directly proportional to the temperature of any given substance, and this is the graph that shows the relationship for this. As you can see here, as the volume increases, the temperature also increases, and for the inverse, if the volume decreases, the temperature will also decrease.
Before the experiment, let's take a look at this graph. It shows how water's volume changes with temperature. Interestingly, when water freezes, it increases in volume, but during the 4 degrees before freezing happens, water seems to contract. This is because at this temperature, hydrogen bonds break and allow molecules to come closer together. Now our experiment isn't going to show big changes in volume like this because the amount of water we're using is going to be less than shown on the graph. Of course, our experiment will still show a change in volume though. Let's get to it. Alright, so in front of me we have 3 identical cups filled with 200 milliliters of water. This one will be going to the freezer, this one will be our room temperature one, and this one will be going in the double boiler, so the glass doesn't explode, which will be shown later. To differentiate all of them, I have some food coloring, which I will be putting this orange one in the one getting heated up because the colors match. And green one going into the one that's getting cooled. As it takes longer for the water to cool, I'll be putting this in the fridge for about 40 to 45 minutes, and I will be watching this until it turns into around 60 degrees. Alright, so the system we'll be using is, as I said, a double boiler, which is a pot with water in it and the cup, because if I just put the cup on the stove, it will explode and glass will go everywhere. So now we wait for the green cup in the fridge to go to around 4 degrees Celsius and this one to go to 60 degrees. Alright, so the water is around it's cooling down right now, but it's at 65 degrees Celsius. Take note that unlike in the picture I showed in the presentation, the change is going to be very, very slight because I did not put that high of a temperature, and also that picture was a bit exaggerating. I have a beaker here to show the distance difference in volume. We're going to do the heated one first because it's going to cool down. Remember, use something to hold it with so you don't burn yourself. As you can see, it comes to around slightly above 200 milliliters. Or it's the angle. And now the water should be exactly 200 degrees. Not 200 milliliters. Which you can see there, or slightly under it because of the angle. But you can see that the red cup has some more volume than the normal water. So I just got this out of the fridge. It is at around 4 degrees Celsius, and it is, going to room temperature pretty quickly. So I'm just gonna pour it in, and we're gonna see the difference. Since this is also a different angle, I'm gonna do the normal one again. So you can see there, little less than 200 millimeters per second. Room temperature water. It is a little more.